review about the audio and figures and video, how we represent them in the computer, and then we go into our hardware representation, the physical representation in this computer chapter. Okay. So firstly about the audio. So human beings take the audio signal through our ear, right? So that is an analog signal. It's an analog signal. But we said in the computer we use digital signal to represent the infinite word, the finite information to represent the infinite word. So we discrete them in this digital representation for the signal, right? Okay. So we use this digital sampling. We use this sampling strategy to digitalize it to obtain its digital signal. So that means we, in a cycle, we measure the voltage. Okay, we periodically we measure the voltage, and then we record the numerical value. Okay, so that is, here is a analog signal. So we do the sampling. We can do such kind of sampling, right? We can also do such kind of sampling. Okay, you can see the difference here, right? This one you need more signals or information to represent this wave, and this one you need just less information. But this one may be more related to the original one, right? So we have a question here is that how often should we do this sampling? So we need to keep its original information, but we hope the less information we represent would be better. So here is at least sampling frequency. It's supposed to be 40,000 times per second. That means each second we need to do the sampling 40,000 times so that it is sufficiently enough to create a responsible sound reproduction. So it may store and produce such kind of audio information. We can hear it just like we hear it from through our ear in our real world. Okay, this is how we can do this class through this website, right? You can hear my voice because the computer do such kind of samplings. Each second it samplings more than 40,000 times. Okay, it is also how you can listen the music. It's similar because the computer do such kind of sampling for the audio information representation. Okay. Okay. So when we do this audio representation, we can use the CDs, right? And we the CDs use these binary digits, so it has some lasers to point at this disk to obtain such kind of signals. And this laser light reflects strongly or poorly if the surface is smooth or pitted. So it can represent 0 or 1 for the binary strings to create such kind of binary strings in these CDs. So we have some kinds of formats. For example, we use MP3 or VQF or WAV, what we frequently used. Such kind of formats is that how we represent these audios. Also, they use some compression approach. Okay, they use some kind of compression approach. For example, they may use half-main encoding. Okay, or other kinds of compression to decrease how much space we need to store such kind of audios. So you may check this question after class and tell me this Friday on our next class. Okay, so in the MP3, such kind of compression supposed to be lossy or lossless, or both. Which one would be the correct selection? Okay, consider this after class or check more reference and find it might be quite interesting question. Okay, so then we talk about how we represent these graphics. Okay, so in fact, we have already mentioned that when we represent these graphics, we firstly use color, okay? So for the color, I think all of you know that if we want to represent color, we use three original color, red, green, and blue, right? So we use how much percentage this red or green or blue is mixed in this color. It may be a different color. So we use three strings to represent how much red and green and blue it's supposed to be here. And this is how we do this color representation. We call them RGB representation, okay? So a color is expressed as an RGB value, and that is three numbers, and which indicate the relative contribution of each of these three primary colors, okay? So for example, we use these 255, 255, and 0 to represent yellow, okay? That means we use red and green and mix them together and no blue. So we get a yellow here. Okay, so because this number is 255, you can think this is 8 bits, right? 8 bits to represent each color, each red or green or blue, how much it involved in this color. So this is a figure is that we use red, we use green and blue, so that we can create all the colors in this in these real dimensions. So we introduce several concepts. First is color depth. That means the amount of the data that is used to represent a data. Okay, the amount of the data we use to represent a color. For example, I said we use 8 bits, or we can use 16 bits, or we can use other string of bits. So it represents how amount of the data. Okay, so a 16-bit color depth represents we use 16 bits to represent the RGB values, right? So in this color depth, in fact, we have 5 bits used for each number in the RGB values, with extra bit sometimes used to represent these transparency, okay? We do some additional representation for this transparency. So for example, in this 24-bit color depth, we use 8 bits for each number in these RGB values, okay? So we get 24 because 8 times 3, right? Okay, so this is our first conception about this color depth. You can check what's the color depth number in your own computer or your own computer devices. It's quite interesting. This is just an example table about what the RGB value is supposed to be and what's its relevant color. You can check this through the computer, and you can get exactly a very detailed table for each color, how it can represent it, how it represented, what's its RGB values through the internet. Okay, so So this is just the computer may use this for you to choose for different colors, and all these colors are represented by these RGB values in different color depths. So we need to recognize another very important concept is this resolution. That means the number of pixels you use to represent a picture. Okay, we have also said in our previous classes that each figure is represented by pixels, okay? That is each dots with each different colors to represent a figure. So how many numbers of the pixels to represent the same number? It is what's the resolution of your computer or your digital devices. This is also quite important because you can see, you may see much more resolution numbers. It may represent a much better or more clear pictures it can do, right? So to store such kind of figures, we also use like bitmap or GIF or JPEG or PNG, what we are frequently used in our daily life for such kind of graphics. So of course, the difference of how we store these formats in different format. The difference is how many how many about this how we do the comparison, or how many does they use, how many bits that they use to represent colors. They have different definition. Okay, so you may check this after class by your interests, and you may consider what's better for line draws or pictures, which format is better for different situation of such kind of figures. So this is also a question we'd like to discuss our next class, okay, this Friday. So consider this after class. Okay, this is an example of about these whole pictures, and this is in its pixels representation. Okay. Okay. So another is a vector graphics. It is a little bit different with the previous one. It is a format that describes an image in terms of these lines and geometric shapes. Okay, it doesn't represent it by pixels of the colors. It is in terms of these lines and geometric shapes. For example, in our when we do the academic research, when we create a article or journal or paper to submit to some journal or conference, when we write them, when we draw the figures, we usually use such kind of vector graphics to represent our figures. So a vector graphics is a series of commands. What kind of commands? It describes a line's direction and its thickness and color. Okay, so it's like it directly define this line, what's this thickness and what's this direction, okay, and what color it is supposed to be. Okay, and then the file sizes of such kind of vector graphics tends to be smaller because not every pixel is described, right? If there's an empty position, you don't need to represent these pixels, right? You only store such kind of lines. So it also has its good sides and bad sides. We are not going to get in this in detail. You may check this after class by yourself. So when we represent the videos, it's similar. It's quite similar to represent the figures. Okay, we just do some compression for these videos. We store a lot of figures, but we do some compression so that we can store such kind of videos. So almost all the video we use some lossy compression methods because we want to minimize the amount of the data associated with these videos, right? Okay. So of course we have different compression like temporal compression or spatial compression. So you just need to know such kind of concepts that when we represent video, we represent a lot of figures, and we use such kind of compression to store such kind of videos. And when we represent figures, we represent the pixels. We use RGB values to represent such kind of figures, or we can store the lines to represent such kind of vector graphics. Anyway, that's the main concept, the underlying concept of this representation.